Well, I can start with some formalities. So I welcome you to webinar by the project MaMMoS, who kindly share with us the output and their journey through the projects they're doing at the moment. And today we have Hans Fangohr with us, who heads the Scientific Support Unit for Computational Science at the Max Planck Institute for Structure and Dynamics of Matter in Hamburg, Germany, and is also a full professor of computational modeling at the University of Southampton in the UK. He is recognized for his training and education in computational science, and as such is joining us today as today's presenter, has experience in high-performance computing and research software engineering. Because as you know, some of our projects based on materials modeling are actually software development, and you develop software with often remote partners, and that requires also like some tooling, which he will talk about. Hans Fangohr is also an educator and wrote a Python textbook and shaped doctoral and postgraduate training programs. And he has contributed and led several open source scientific software projects, particularly in the micromagnetic and computational physics communities, including NMARC, FIDIMARC, and UberMARC, as well as tools supporting reproducible science with Jupyter Notebooks. And he has co-authored more than 180 publications. So Hans today with his talk wants to do it interactive. So he will invite questions as we go along at a suitable time. And so I have to point out to you that we tape this talk, which means we cannot really cut out contributions you make during the talk. Yeah. But on the other hand, it's quite good because that makes it interactive and engage an audience who later would like to listen to it. So there's an educational value in every question I'm sure you pose. If you don't like this, you can put your question at the end of this talk. This is when we cut them out. So just point it out. But as I said, it's very interactive. It's a joint undertaking, and you're very welcome. What I'm doing now is I put you now into the capable hands of Hans Fangohr. And Hans, please, the audience is yours.
Thank you very much. I'm still fiddling with the video settings. I'm trying to see the faces of people as we deliver this talk so that I can try to adapt to puzzle faces, board faces. And just be a bit more flexible. So I'd encourage those who want to co-determine the speed of this to switch their cameras on and let me see their expressions. But of course, you can also just listen without being seen. Okay, similarly, I'd encourage questions along the way, maybe just write in the chat or speak up, and that might make it easier to respond to queries immediately. All right. Let's go. We're looking at about an hour, not more, for this, and we'll have some interactive examples as we go along. Here's my outline. We'll see that what I really want to describe is this pixi tool for software installation, and this can install conda packages and pip packages. So we'll talk about those first and then bring them together before we comment on some additional material. This is part of the MaMMoS webinar series, kindly hosted by EMMC and been funded by this program. What is the scenario I want to consider? I want to look at two cases. The first one is where somebody needs some software to carry out a task. For example, maybe I need to install some Python packages to plot some data. And we look at how we can install software for that and how pixi can be useful with this. The second scenario, for which we'll only have 5 minutes at the end, is the situation that somebody wants to develop software, and in particular, we'll be looking at a Python package here. I'll put quite some emphasis on Python because it seems to be a tool that is used nearly everywhere nowadays. Okay, I already said that this was our plan. We'll be looking at pip and conda and then pixi, and start with a motivation. Why is it important to be able to install software? If you come from the fair point, we want our work and our data to be reusable, and reusable for me also means reproducible. And for both of these things, if I want to do something that involves software, I have to be able to install the software. You can also look at this more generically and say it's very hard to imagine a situation where you can carry out your scientific work without software, be it just for capturing some data or plotting it or analyzing it, or if you run a simulation that's of course particularly prominent. Why is this hard to install software? For many years, I had the feeling I was the only person struggling to install software on, say, high-performance computing systems that make files and configure stuff and things doesn't work in libraries. But it turns out it is actually a hard problem, and most people suffer with that. So imagine the tasks we need to do is either to install a Python package or perhaps to compile some source code on some larger system. Why is this difficult? I think there are two aspects to this. One is that it is just a complex problem, and in science particularly so, because we often combine many dependencies. We need fast execution, so we get additional complexity through parallelization or particular hardware. We may have different versions of libraries that we depend on which conflict with each other. And then in addition to that, also in science, we are not being rewarded for packaging our software well and making it easy for other people to reuse it. If I have the choice to polish a piece of software that I've used for some work, or I start to write the next paper, then generally the next paper will look better on my CV. And I think that's also part of the problem why, in particular in academia, the installation of software may be hard because either we don't know how to do it well or we don't get rewards for it. I want to introduce one educational example for which we will install the needed software later on. This is a hypothetical research result where we imagine that this is a figure that goes into a report, and the relevant data files are in this GitHub repository. We can have a quick look there. So we are on GitHub, and here is a particular repository which contains several files. One is this one, which contains the data we care about. We have one row per country and then different columns with number of deaths attributed to COVID-19 as a function of date. And there is a Jupyter notebook here, which will read this data. So here it's being read, and then it does some post-processing on this, and it creates an intermediate result, which in general maybe you would call a reduced data set. So this is what we're actually interested in for the plot. And then it does a bit more smoothing of that, and in the end creates this figure we're after. So this repository is the attempt to make this figure creation reproducible by gathering the data file and also a recipe how to do that. So in a more systematic view, here's the data file, and we process it into this intermediate file, and then we process it further to get the figure file. And for reproducibility, we need the original data file, and we need to know how to process it. And we also need to know what software is needed for that processing, and we need to be able to install that software. Okay, And in this case, the required software is detailed in this file and also in that file. And we can come back to that a bit later. Do we have any questions or comments at this point? Okay, then I want to comment on how we install Python software. First, the most fundamental way to install a Python package would be to use the pip command, so pip install, and then provide the name of a package. This package would have to be available from the Python package index. All of this only works if Python is already installed on our system, so we'll just assume that is the case for now. And then there is a variation on this, that with any installed Python, I can use this virtual environment module, which allows me to create a virtual environment and then use pip inside that. We'll look at an example in a moment. There are a number of higher level tools that internally may use this, such as pyenv, uv, or poetry. This is a typo here. Conda and pixi, and they can all help us in managing these Python packages and Python environments. If we look beyond Python software, so if we're interested in installing other software, there's a number of different approaches. There is conda, which we'll talk about more later. If you work on high-performance computing systems, then you may use spack, which essentially compiles all software from source. This is great to tune the software for the hardware. There is Nix, which is been created with focus on reproducibility. Some people say it's not so user-friendly. Then we have software management systems from the different Linux distributions. We have similar tools on the Mac and on Windows. Or you could also put the software into a container and then run this container on your host system, so that some of the complexity of that software management is hidden in that container. That's just to provide an overview of what is out there and where we're sitting. And perhaps also I want to mention a few possible metrics. How do you assess the quality of a software distribution or installation system? One of those would be, can I have multiple environments on the same machine? So could I install Python 3.4 and 3.10 at the same time on the same machine? If I have a Linux distribution such as Ubuntu, I couldn't do that. I can only install one of those at the time if I want to use the apt manager, for example. Another question would be, can I somehow lock this configuration and recreate it? Can I save it and on a different machine later on recreate the same environment? Does the method I use allow me to install the same software on multiple operating systems? And also sometimes the computation of dependencies is hard. I need some package. This depends on a few other packages. They depend on something else. And all of those may have constraints, which versions work with which other versions. And solving this optimization problem can take a long time. And so if this happens quickly, then it's nice. Maybe not essential. We could all wait and make a cup of tea, but it's also nice if that happens quickly. That's the end of my introduction and trying to put this into context. And we'll now look into Python package installation with pip and virtual environments. So as an example, I want to imagine that we want to install a package called cowpy, which is available in the Python package index. And perhaps we just try to do that. So on this computer, I'll go into the /tmp directory so that everything in here will be deleted when the machine reboots. And let's do this in a subdirectory where we use pip and we install something called cowpy. So if I want to use pip, I need to have Python already in the search path. I can check that with the command which, and there's no Python here. Now, in this case, it's called Python 3. This sometimes happens. And this Python 3 interpreter is something that on this Mac I installed with a tool called brew earlier. And it just lives there. And all the users of this machine can see this Python. And as I have that, I can follow these instructions to create a virtual environment. I'll explain in a moment why exactly we want to do that. So this -n tells Python to use a module. We use the venv module that comes with Python. And then I can provide a name of this virtual environment that we're now creating. We may not quite know what it is yet, but let's do it anyway. And when I execute this, this creates a subdirectory called myenv. And in there we have a virtual copy of this Python that is installed under this location. So it looks like it is a copy, and some of the files are just links. So when I look at the file size of this directory, it's 12 megabytes, which is not particularly big. And in this subdirectory, there's now my virtual environment, which I need to activate with this command. So I say from that bin directory, there's an activate script. And once I've done that, I get a hint here that I have activated this environment. I can now ask, do we have a Python? And it tells me, yes, there is something. And where is it? It's in the /tmp directory. And this was the directory path I created. And then in there, there's this virtual environment, and it has a bin folder. And in that, there's the Python. And with that Python also comes a pip executable. And this we can use to install a Python package. So I can run pip install cowpy, for example. And this pip command goes to this Python package index, and it looks for a package called cowpy, and it looks for the most recent version, and it will download that and install it in this virtual environment. And as a result, I now have an executable called cowpy in the path. This is a feature of this Python package, that not only is there a Python package which I could activate using import, it also puts a script in the search path, which is called cowpy. And the purpose of this is to send us messages. And I have forgotten the precise syntax. I think we have to say, there's some text. And then it gives us some ASCII. Oh, I was wrong. We don't need the -t. I think the -t stands for thought, which is why we have those thinking bubbles. Let me remove that. Aha. And now this way, the cow is just speaking. If I want to use this environment later again, so here's a new shell, I would need to do what is shown on the slides here. I would need to activate this environment again. So I go to this directory where I assume this is where my research work takes place, and for that I may want to use this virtual environment. So I need to activate it again, and only once I've done that, let's not execute this, let's just confirm first we have no cowpy. Then we activate this virtual environment, and now we have this executable in the search path. Okay, so that's the most fundamental way, and manual way perhaps, of creating a Python, installing a Python package. Now, why did I use this virtual environment? And there are a few reasons for that. First one is I used this Python 3 coming from Brew, if you remember here, where here it is, where I said all users of this computer could see that Python. I don't want to make that dirty by installing a package in there. Maybe nobody else is interested in CowPy, and I'm not really interested either. I'm just pretending only. So it's cleaner to do that in a local environment in which I can isolate my dependencies. I can do within this virtual environment whatever I like. I cannot break anything else. It also means I could install dependencies in there. I could install a particular NumPy version, which might be different from the NumPy version that Brew perhaps has installed already. If I don't want this environment anymore, I could just delete this folder that we have created here, and then it would be all tidy. And if I need it again, I would need to repeat my pip install command. If I were to install CowPy into this global Python, it would be a bit more messy. And therefore, we try to avoid that. Okay, any questions? Marvelous. Okay, so we could then also try to work on this reproducibility example. How would I install the software for that? This is what I showed you on Git first. I would clone this repository. In there, there's a file called requirements. This is a standard way to express Python requirements. So I could, as before, we're still in this virtual environment. Okay, I might just use this virtual environment. Perhaps, in fact, this is a good moment to show there is a command to see what packages we have installed. And I should also be able to uninstall CowPy. Let's tidy this up. I say, yes, please get rid of that. What packages have we installed? It's just pip itself. And I did show that we have this requirements.txt file, which specifies to reproduce this plot, I need the pandas library in version 2.3.2 and so on. And the syntax to use with pip would be to use -r, which means from the following file, please install the dependencies that are listed in there. In this case, this is a slightly longer list because it includes packages that depend on other packages. And so we have to wait a moment for that to install. While we do that, I go back to this Git repository. This has a README file, and in the README file, it says how we could install the software. So this is now showing exactly what we've done. We've done this command already for the CowPy business, and now we're installing the requirements like that. And it also has some information how to recreate this figure 1, and it says we should be running this particular command here. Okay, so the installation has finished. I can take the command from the web page, which basically calls the Jupyter Notebook converter tool, and it will then process, let me see if I can make this even bigger. It will then process, oh, this doesn't help with readability, sorry. Let's try this again. It will process this notebook on the right here, and as it does that, it will execute it, and in the process, it will create this figure1.pdf, which is saved at the end of the notebook. So the window is better for me if it's smaller because I have some Teams elements floating around in the way here. So we're just waiting for that command to complete. because this uses matplotlib internally, it probably has to create font caches, and this needs a moment to execute. Okay, we have some output here, so it's working on that. And when it's done and I look at the files on the disk, we see that most recent date is 1456, so that this figure1.pdf file has been created. Okay, so that was one example. How to install software with pip directly. Let's move on from there. I want to talk about conda. A conda package or conda environment is not specific for Python. We use conda to install Python packages, but that's only one of the things it can do. With conda, we can install any software if a conda package is available, including compilers, Python interpreters itself, and so on. A conda environment is like a virtual environment. It's an isolated environment in which I can install software. This is defined by a list of packages that are installed and a channel. And channels are collections of conda packages, and we'll talk about two here. One is called conda forge, and another two are anaconda and main. And we differentiate those by either being maintained and verified by the Anaconda company or by the community. I'll get back to that in a moment. Many Python packages that are on the Python packaging index are also available as conda packages, but it works this way. It's rare or impossible to have a conda package without a package on the Python packaging index. The dependency management between conda packages is a little bit better than within pip, so this is nice. And to install a conda environment, I need to use the tools either coming from the Anaconda distribution, which I assume many people will know, or from alternative tools such as MiniForge, Mamba, MicroMamba, or Pixi. All of these can also install conda packages. Let me try to comment on the names we've used. Conda can mean at least two things. One is the package format for binary packages. The other is the name of a command line tool to install and manage these conda packages. And then we also refer to Anaconda. There are two things here worth mentioning. One is anaconda.org. This is a website hosting conda packages, both the community and the Anaconda verified flavors. And then there's anaconda.com, which is the website of a company called Anaconda, which has pushed forward all of this tooling, but charges for some of the Anaconda verified packages, the use of that and the use of their tools. And let me get back to this charging situation. For many years, the Anaconda distribution was free to use for most people, and there has been a, for academia, important change in 2024, where it's now the situation that if your organization has more than 200 staff, then generally you should not be using the Anaconda distribution unless you have paid for a license. There are a few exceptions if it's purely for education, but if you do research at a university, then you also would need to pay for it. Not restricted is the use of the conda package format itself, the use of the conda packages in this conda forge channel, and also the use of the alternative implementations of the conda installer. Okay, I think that closes my little comment on conda. Do we have any? Oh, we don't. We do have an example. Okay, let's do that. So I will not execute that, but just talk about it. So if I have a conda compatible tool installed, I may have an executable called conda, or it could be called Mamba. And then I could say I want to create a conda environment. I need to give it a name. And then I can say in that I want to install Python and CowPy. And that would then do some work and create this environment. And before I can use it, I need to run the conda activate command and provide the name of this environment. And once I've done that, I then have CowPy in my search path. Okay, we'll skip that. This is a slide that shows how you could install this reproducibility example. It's basically the same, but you can specify particular versions that you want to install as well. Okay, then I want to move on to pixi for software installation. We'll repeat what we did before. We'll create a pixi environment and install CowPy in that, and I'll try to give some explanations as we move along. So we go back to our terminal here. And first I want to deactivate this virtual environment. We can see it's still active because I have this thing here. So at this point, I've lost my CowPy and I want to create a new folder here. So this name I choose, I want to say it's, oh, maybe we call it CowPy in pixi. Then I go into this folder and now I want to install my software here. So the first thing I do is that I say, pixi, please install something here. Before I do that, I want to show you that this directory is completely empty. This shows the contents of the directory. -r means show them in a long way, and -a means also show hidden files, A for all. And then I would say, pixi, please, let's create a pixi environment here. And I get a reassuring green tick, and it tells me a file has been created. And let's check what actually has happened. Indeed, this file has been created, and pixi has created 2 more files, which are information for Git. If I want to use Git, it tells it what files to ignore that pixi may create. We can ignore that here. This pixi.toml file, let's have a look at that. In fact, let me try to use something called bat rather than cat, because that has output in colors, so that's slightly nicer. This file pixi has created for us. I think it has gotten this information from my Git configuration. It says if I install packages and I don't do anything else, it would install packages from the conda forge channel. It has decided on a name, which is just the name of the subdirectory here in which we are. And it has identified that we are on OS X as the operating system and an ARM64 architecture. It has decided this is my software environment version 0.1. Why not? And there are headings for tasks and dependencies, but they're empty. Now, if I want to use Python, I need to say that I want to add Python to this installation, because at the moment there is nothing in there. And I want to say that I want to use Python 3.11, for example. Then I press return, and pixi will go by default to the conda forge channel, unless I say anything else. Yeah, about the version. So I just type pixi add CowPy. If I want to use those, I need to activate the environment. One way to do that would be to say pixi shell. In this moment, we jump into this environment. Again, we can see on the left that this is the case. And I should have the CowPy executable in my search path. So as before, we can test that it talks to us. maybe. It does. Let's have a look at the location where this executable lives. Hello, I'm back. Is it only me who's in trouble with the network?
Yes, you decided to leave us briefly, but there you are again.
That's so weird because the machine that left you is the one connected to an Ethernet cable. And you can still see the laptop on which I'm working here. Never mind. So the cow talked to us and it's working, and I said we should see where this cowpy executable is installed. It's in a folder called .pixi that has been created. And because of the dot, this is a hidden directory. If I just ask for the contents in this directory, I wouldn't see it. But if I ask for -a, I can see it. The subdirectory here. And this is the place where pixi installs all the Python and the further dependencies. As before, let's check the size of that. This time it's more substantial because it cannot reuse a Python that is already installed on the system. Let's also have a look at the state of this pixi.toml file that we looked at before. It has changed slightly. Under dependencies, we now have two entries here. We have Python, where I specified that we want exactly version 3.11. That's not a question. Oh, this is the wrong language. Thank you. And we have also installed the cowpy package, and here I didn't specify which version I want, and pixi has decided to take the most recent version, which was 1.1.5 from the Conda Forge channel. And it has chosen to add this constraint so that if I later reuse this pixi.toml file to install the same environment somewhere else, all it wants is that I use a version of cowpy that is at least 1.1.5 or newer, but not version 2. The idea there is that version 2 may introduce incompatibilities, and therefore this is not a good idea. This is a working assumption from the pixi team. I think it works well. If I wanted a particular version, I could override this. Let's see what my slides say. We talked about this .pixi subdirectory. We looked at the pixi.toml, which basically defines the environment I want to have. And then there's another file, pixi.log, which we didn't look at yet. This is a more detailed file that tells me that we are on this architecture, and then there's a very precise list of all the things that have been installed. And if I want to recreate exactly this software environment again, then I need to preserve this log file. And I can give that to other people and say, install what is in there using pixi, and they should get exactly the same environment. Pixi provides a command called list, which shows me an overview of what we have installed. It shows in green the tools that I requested, Python and cowpy, and all the other entries are dependencies that Python and cowpy needed. We can also see that these are all conda packages, and we can see that the source is from Conda Forge. Okay, I'm meant to show you some more things. Pixi.toml contains a set of instructions to install the software environment, and pixi.log contains a fully reproducible, more detailed record of what we've done. which of the files I want to use depends on my use case. Often it's quite good if, so imagine I use this CowPy, I use this project for months, I install it on different machines, a new version of CowPy is released, maybe 1.2, and there's a bug fix in there, then it would actually be good to install version 1.2, and for that reason, it's good if the package version is not exactly fixed here. So sometimes that's what I want. Let me leave this pixi environment by typing exit, just to confirm we've lost CowPy, but of course all the files are still here. Let me undo this installation by deleting everything in this pixi subfolder. So now all we have left is this pixi toml and the pixi log file. If at this point I ask pixi to activate this software environment for me, it will look if there is a .pixi directory, and if there isn't, it will check pixi.toml for what I need, and then it will swiftly install that. That was very fast, and then show me that we're in this environment. The second installation just now was so quick because pixi stores a local copy of all the important packages. So this is cached, and that can be quite convenient. I can also change versions of the installed packages. So if I wanted to change something, I would say, please let me add CowPy again, but this time in a different version. I don't actually know which versions exist. Let's try 1.1.0. Okay, that seems to work. So if I ask again for the pixi list, we can now see that CowPy is installed with version 1.1.0. I can do the same with Python, so I could change the Python version and say, let's use 3.14 perhaps, and then it will download that. That takes a bit longer because we haven't done this before, so it's not cached. And if we look at the pixi list of installed packages, we still have CowPy 1.1.0, and Python has been updated to 3.14. Okay, now I did say that pixi can install conda packages and also packages from PyPy. That's what we look into now. There is a similar tool to CowPy, which is called cowsay, and this is only available from the Python packaging index, so not available as a conda package. To install that, I also use pixi add, but this time I need to say that I want to install from the Python packaging index. And then I provide the name of the package, and pixi adds it to our pixi environment. I can ask for the list of packages. Now we get a new color here, and we can see that this is a package from PyPy. And it should also be in the search path because we are in this environment. And this cowsay has a slightly different user interface. It needs to have a -t for text to be spoken. Okay, so we can install packages from conda and pip in the same environment. Let's have another look at our pixi.toml file. We can now see there is a new section here, which are the dependencies from PyPy, and cowsay is within that. By the way, if I prefer to modify this toml file directly with an editor, I can also do that. I could say, after all, Python 3.11 was a good choice. I'll save the file, and now I need pixi to notice that this has changed. So let me try to say install, and it will now go back and install Python 3.11, as this is what I requested. and we keep all the other packages. Okay, any questions? Okay, then let's look at installing software for multiple platforms. We've seen that pixi has recognized that this is the platform we're on. Platform is the operating system and some hardware information. And now I want to imagine that I also want to use the same software environment on a Windows machine later. Then one thing I could do is that I take this command from the manual, which I'll explain. So I'm saying, dear pixi, for the current project, let's talk about platforms. We want to add a platform that is called Win64. I need to know that Win-64 is the right string. And when I do that, pixi will check if all the packages we need are also available for Windows 64. It has already done that and provided a tick here, and we can see some indications of that. First, in the pixi.taml file, we can see that under platforms, we now have also listed Win64. And it has also updated this log file. There is now one section here for the Macintosh platform, and there's a second one for Windows. So for both of these operating systems, we know all the locations of all the conda packages and also the packages from PyPy that are needed to recreate the same environment. I'm not a fan of this very long command here, so what I prefer to do if I need this is to just have the right strings that describe the platforms, and then I edit this file and I say, please also compute the dependencies for Linux 64 and for the Intel Mac hardware. So let me force an update of this, and then pixi has thought about the dependencies, and when we look at the log file, we now have a Linux section as well, and the OS x64 version and so on. This is super useful if you are in the situation where a package does not exist for a different operating system, for example. That can happen. And this way I can find out that this problem exists even without trying myself, because the dependency calculation from pixi is carried out automatically and will do the work for me. Okay, here's a summary of the role of these two pixi configuration files. I think I tried to explain this along the way already. The pixi.toml tells what I would like to have, and perhaps I'm not fully specific with the version numbers. Maybe I allow a range of versions that are okay, because I may want to use a particular version or newer because I want to benefit from the new features. Although I could pin this down absolutely if I really wanted. But in any case, there is the corresponding pixi.log file, which makes it possible to give me an exact copy of that environment. Now, if I want to use that, I can use pixi install with the addition -- frozen, which will tell pixi to ignore whatever is in the pixi.toml file and just install everything that is listed in the pixi.log file. And if for some reason this doesn't work, it will fail. It will not try to recompute any dependencies. So when I work on a research project or a software package, then I should keep both files. This one I should definitely have because it contains my intention, and perhaps this is sufficient. But if I need the best possible reproducibility, then I also need to add this pixi.log file to my software setup, my repository, my data set, my reproducible publication. I want to comment on one more feature of pixi that can be quite useful, and that is the story of tasks. So we can tell pixi that we want to create a task. A task is like an alias for a more complicated command line. And we want to add a task, and we call the task, maybe say hello, maybe like that. And then what we want to do is that we use cowpy or cowsay to say hello. Let's see if that works. Perhaps I have to use quotes here. Okay, so pixi says it has added a task, say hello. If this has worked, I should be able to say pixi run. Run always means run a task. And then pixi tells me it is running the task I asked for, and it executes this command inside this pixi environment. This is a bad demo because we're already in that pixi environment. So let me exit that environment. So it's now not active. I cannot see the cowsay executable, but I can say pixi run, say hello. And just for the execution of that task, we'll activate the pixi environment and then leave again. This task is recorded in our pixi.toml file here in this tasks category. And there is just the string that we've used. As before, I could also edit the file and put the task in here manually. And these tasks can also manage dependencies in some lightweight way. So it's a little bit like a makefile where I could have multiple tasks that depend on each other. And I can basically summarize a complicated procedure in such a task. Okay, let's go back to this example that we had before, the reproducibility example. I try to clone that repository. This creates a subdirectory, so I wouldn't have to create this. And this repository already has a pixi.toml file. This was hosted on GitHub as part of the repository. And if we look into that, we see it also has a task defined, and the task is called reproduce, and it does the work that is needed to create figure1.pdf. So we've just downloaded this. We have not installed any software, but I can tell pixi to run this reproduce task. And before it can do so, it needs to install the software environment, which it does here. And that takes a little moment. And once it has done that, it will run this task, create figure1.pdf. And then we have completed this process. This is really very convenient because I can make this whole reproduction even more automatic. Now I would just need to tell the user, please install pixi and run pixi run reproduce, and we get to this. Okay, this needs a moment to finish, but it's underway. For our MaMMoS project, one can install it using these commands. What are we doing here? So this is finished. Let's call this MaMMoS. So we create a pixi environment here. We know from the instructions we need Python and JupyterLab. And once this is done, we install the MaMMoS package, which is on PyPy. So we need to add -PyPy. And once we have this, we activate the environment. And then we have a tool that is in the path, which will download the examples that people would need to play with MaMMoS. Now this takes a bit longer, so we just keep this running, and then we could start a Jupyter notebook in this environment and explore those examples. It's an example for use of pixi in our ongoing work. Okay, so here's my summary of how we use pixi for software installation. We can create a pixi environment. All the software is stored in the subfolder.pixi. We can add packages like this. If they're coming from PyPy, we need this addition. We can fix versions or change versions. We can define tasks. We can compute dependencies for other platforms. And using the pixi log file with a frozen argument, we can reproduce installations exactly. This is more useful as a reference. I want to talk 3 minutes or so about using pixi for software development. Are there any questions on this? Using pixi to install somebody else's software section. Then we move on. So the scenario now is that we imagine as part of our research, we develop a Python package. And when we do that, there is a file called pyproject.toml that is important. And let's look at an example. This is from one of the Python packages developed within the MaMMoS project. This is an abbreviated version so that it's not so long. It knows about the name of the package and the version number and which Python it needs and what other Python packages it might need. And beyond that, there are some entries here which refer to a tool, and in particular the pixi tool. And these are settings that we can use for the package development. So in here we can say we need particular tools like pre-commit or pytest or rough. And we also have some tasks that occur repeatedly. For example, to run the tests that come with this package, we have an alias called test unit test, which would then call pytest -v tests. And if I want to run this, I can just use a pixi run if I want to. And test all would in order run the other tests that are defined here. Now, how is that helpful? Because if I want to work on this package, which is hosted on Git, what I would do, oh la la, yeah, I can comment that in a moment. Let's say package development. I clone the package I want to work on, which has been cloned into a subdirectory. In there, we have this pyproject.toml file. And this is now a bit longer than we saw before, but at the bottom, we have information for pixi, including the pixi tasks. Now, if I do some changes here, then I would want to see, do the tests still pass? And sorry, we're still in this MaMMoS environment, which I should leave. So I need to go back to this location here. This is where we've just been. And I can say, pixi, please run those unit tests for me. And the first thing it will do is to install all the dependencies that the package itself needs, and then the packages we need for development, like pytest. And when it has done that, it will execute the task that we wanted to run, which is this one, pytest -v tests, which is happening now here. And then hopefully we get to see lots of green lights so that everything is okay. And while it does that, I want to comment that the nice thing is that in the continuous integration, so the automatic execution of these tests on GitHub, we have the same command where we say pixi run test unit test, and then on GitHub's workflow, pixi will install the same environment that I have locally just from this command. And so I can be very sure that what happens in the continuous integration is the same that happens here. and that helps me in finding mistakes. Okay, that brings me to the end. I've taken this little graphic here from the pixi homepage. We've talked about the ability to reproduce software environments. I've shown you simple task examples. We said we can compute that all the dependencies we need are available on multiple platforms. And I've shown you how pixi can be used in development of Python packages. We didn't really talk about those things here. The main message is with pixi, we can combine packages from conda, forge, and pip. And we looked at the use cases of installing somebody else's software and using it, or developing our own Python package. And that's all I had planned to say. Thank you for your attention.
Brilliant. Thanks so much for the talk. And we do have actually a question. Can you read the chat, Hans, or shall I read it to you?
I can read it. If I want to run different things, unit test and others, using pixi run, each time we'll download dependencies. Good question. No, maybe I didn't present that clearly. When I use pixi run, it will install the dependencies if needed. But once they are installed the first time and there has been no change to the pixi.toml, it will just reuse what is there before. But you could also, instead of using pixi run, you could use pixi shell and just type the commands in there. They're completely equivalent. It's just a preference, what you find easier. Okay, great. I assume that is answered, and I move on to the next question. What is your recommended way to install pixi? Pip, conda, or directly download? Okay. I would download pixi directly. They have a section on this. It's basically on Linux and Mac copying this command, and on Windows there is an installer. And if you don't trust that script, they also show you what it does. But this seems to work quite well for me. And pixi has also a command that goes, I think it's called self-update, and then it will update itself. Indeed, so we've just done that. We've updated pixi from version 0.59 to 0.61. Okay, second question. Can pixi replace container-based software, e.g. Docker? Difficult, perhaps not completely. I don't think it can do significantly more than, say, a conda environment to which you install things with pip. It's better in that it can manage both the dependencies from pip and conda, at least a bit better. And we have the tasks with the dependency engine. And I also like that by default, it installs the software in a local directory. So I have it close to the files I want to work on. This fits my personal style. It depends a little bit what you do with a Docker container, I think. So I'm not quite sure about that. Question 3, can pixi help generate GitHub Actions CI/CD YAML file? I think it can simplify your GitHub Actions, because when you have a pixi.toml or a pyproject.toml file with pixi information, then you can use the pixi run commands within the CI, and this will then already take care of the software installation, so that you have the same software installation procedure as you would do locally automatically, and you can reuse the same thing in the CI, and therefore it makes the CI script a bit easier. Yeah, I hope that was addressing.
Yep, so there's 2 thank yous for you, so that's good, yeah. So I think this tool seems also interesting for sysadmins, because what a sysadmin really hates is cowboy installation and background jobs. And basically by looking in your pixi tom file, they can see what you have done and where the libraries are going end. So that's actually quite a nice tool. Yeah. So let's ask the audience something, because we are mean. Who in the audience has used pixi before? You could raise your hand, actually. There's this little hand tool. Let's see who has used this. Okay, yeah. Okay. Okay. So we've got 3. Okay. And now we ask another question. Who of you would be interested to use it? Okay. No, see, that sounds, I mean, it sounds like a nice tool. It is, so my Unix is quite in the past. So I indeed have worked with make files before, obviously, and hunting libraries and writing paths in a bash file, which I could source at some point, but that's long time gone. And I was really good in running background jobs when I knew the sysadmin would go home. But you shouldn't be doing this, of course. Brilliant, yeah. So we have information on our webpage where you can find pixi. So there's some links, and obviously you can help yourself to get started, hopefully, for those of you who want to look into. Okay, so yeah, so thank you very much, Hans, for your nice talk. I didn't expect to see command lines and ASCII cows today, but there you go. Was really nice and a good hands-on introduction of what needs to do. And from the MMC side, we also thank the audience for taking part. It's our last event in 2025. So we wish you all a happy Christmas if you celebrate, and otherwise happy holidays, and definitely to all of you a happy new year. And our MaMMoS series and other webinars you can find again in 2026. So stay tuned with us. So we know from MaMMoS there's some more interesting things to come for sure. And then join us again next year. So thanks so much for participating, coming, and for Hans to give us this brilliant talk.
Thank you very much. Thank you.
Thanks so much. See you all soon. Bye.